So now we have the presentation from João Brito, who will tell us about semi-classical Bremsstrahlung from a charge radially falling into a Schwarzschild black hole.
So thanks for the introduction. Hello everyone. With this oral communication, I would like to talk about semi-classical Bremsstrahlung from a charge that is radially falling into a Schwarzschild black hole. So this presentation was based on a paper published in Physical Review D in collaboration with Professor Bernard, Professor Iguchi, Professor Crispino. So our main objective with this work was to investigate semi-classically the radiation that is emitted by a charge that is radially falling into a Schwarzschild black hole. So in order to achieve this objective with this presentation, we needed to review the dynamics of the electromagnetic field in Schwarzschild and obtain the one particle emission amplitudes. And with these amplitudes, we study the radiation that is emitted by the charge. So we separate our results into two parts. So the first part is the analytical part, where we obtain some analytical results in the zero frequency limit, and the second part is the numerical results. So with this short presentation, we aim to answer questions such as if the spectra of the emitted charge depends it depends on the initial parameters, that are the initial velocity of the charge and the initial radial position. If there are any connections with the black hole quasi-normal modes or quasi-normal frequencies, and if the zero frequency limit results can be used to estimate the radiation that is emitted by the charge. And in the end, we will talk a little bit about issues that appears in the point particle model. So the dynamics of the electromagnetic field in Schwarzschild can be derived by the following action. So here we have the Lagrangian and the Feynman gauge, where F mu nu is the electromagnetic tensor, as usual. G is a gauge term, and the vector K here is introduced for convenience. So basically, we obtain the Euler-Lagrange equation in this way, and the positive frequency modes. These modes are characterized by some indices, the polarization, the angular quantum numbers, the frequency, and this index N that stands for the so-called in and up modes that Rafael told us early today. So we have four kinds of polarization in this case, but we will restrict ourselves to the physical polarizations that will be used to construct our physical modes. So more on these four kinds of polarization, I refer you to these two papers here. And here we have the physical modes. I would like to note that only the first mode has non-vanishing component, non-vanishing radial component. And this mode will only this mode will couple to the current associated to the falling charge. So the quantization of the electromagnetic field is a little bit similar to the scalar case that Rafael told us early today. So I will skip this part because of the time. So the infalling charge is described by this current here. So it has a full velocity given by this expression. So here we have the killing energy of the charge that depends on the initial position, the initial velocity as well. And the radial velocity of the charge is described by this expression as seen by the asymptotic observer. And when the initial velocity obeys this inequality here, So the charge only decelerates while it falls into the black hole. So this is basically a geodesic analysis of the space-time. So once we have the quantum field and the classical current, we couple into this interaction-action term, which we add to the action, and this will give rise, for example, to the emission amplitude or absorption amplitude and so on. So here we have the usual vacuum state, one particle stage, and the total action. So with this emission amplitude, we can study the probability of emission of one photon is basically the radiation emission, the classical radiation emitted by the charge in this case, at this order in the perturbation. So here we have, with this amplitude, we define the partial energy spectrum and some other related quantities, such as the total energy spectrum and the partial and total emitted energy. So explicitly, we have this expression for the partial spectrum. So as we can see, we cannot find a closed form to this expression because here we have a T that is a large expression, so the radial modes, but we can do so in the zero frequency limit. So in the zero frequency limit, the radial modes can be written in this form, where C omega is a normalization constant, B in this case is a known constant, so such that explicitly we obtain this for the partial spectrum in the zero frequency limit. Here, F is the Gauss hypergeometric function, and as you can see, this spectrum vanishes if for vanishing initial velocity. So of course we can compare these with the numerical results, and we find a good agreement. Now we can continue to analyze when the charge falls from infinity, but now we use numerical methods to see what happens with the spectrum for general frequency. So here we see that the spectrum vanishes in the zero frequency limit. And here, I don't know if you can see, but there are some vertical gray lines here that corresponds to the black hole quasi-normal frequencies. So here we have the fundamental quasi-normal frequency, and as we can see, the spectrum decays exponentially. This is a log scaled plot, so the spectrum decays exponentially for larger frequencies than the fundamental quasi-normal modes in this case. So we can make some other conclusions, such as the multipolar distributions. In this case, the radiation is mostly of dipolar origin. We can also investigate the influence of the non-vanishing initial velocity, in this case, for an ultra-relativistic charge that is falling from infinity. So we see that the spectrum is almost flat up to a cutoff frequency. So this cutoff frequency turns out to be the black hole quasi-normal modes. So recall that the charge only decelerates in this case when it is projected from infinity with velocity close to the velocity of light. So here we can also analyze the multipolar distribution of this radiation, the fraction of this energy that is associated with the initial killing energy of the charge. But now, once the spectrum is flat, up to a cutoff frequency, that is the quasi-normal frequencies of the black hole, we could use these insights to estimate the energy that is emitted by the charge, for example. So we can do this by using the zero frequency analytical results and the quasi-normal modes of the black hole, and these agree very well with the numerical results. This is very important in the limit where V is much closer, is very close to to 1, and for the multiple number going to infinity, because in this regime, the numerical calculation is breaking down. So we can do more. We can construct the spectrum using this insight. For example, if we consider that the spectrum is a sigmoid-like function in this case, characterized by the zero frequency results here, the zero frequency value, and the quasi-normal modes of the black hole, and also characterized by a additional negative constant in this way. So we can reproduce the numerical results, and we can do more. We can go any further than the numerical results, and this is very interesting in this case. So we can also verify the influence, the case where the charge is released from a finite distance from the black hole, in this case from rest. So we consider the case, the charge falling from the photosphere in this case. The quasi-normal modes of the black hole play a part in this case because it is almost the position of the maximum of the spectra. So, and as a general rule of thumb, the peak of the spectra shifts around, the spectrum shifts around the quasi-normal frequencies, the quasi-normal frequency of the black hole. As we go to higher values of the initial position, smaller values of the initial position. So we can now investigate the multipolar distribution of this radiation. It is mostly of dipolar origin, as before, and this dipolar contribution increases as we increase the initial position of the charge. Now, the point-particle model that we are using has some problems. So, for example, it introduces high frequency into the problem. So, and when we consider the structure of the charge, these high frequencies are cut off. So, we can get some insights into this by considering, for example, the case where the charge is a string that's falling to the black hole. So, here we have this string is composed of any non-interacting particles, each with charge Q over n. So when we release these charges one after another, so phase effectors appears in the emission amplitudes that is associated with each charge. So these when we take the limit of n tends to infinity, this will produce this multiply factor here in the partial spectrum, and this additional factor decays as 1 over omega squared. So this completely governs the behavior of the spectrum for higher frequencies, as we can see applying it to a test spectrum, for example, in this case. So also there is no radiation here when the wavelength of the radiation is equal to this temporal size of the string here. So we have this behavior for the. So I think that's all for today. Thank you very much.
Thank you, João. Any questions?
So regarding the title, it is Bremsstrahlung radiation, but so you show the flux. How is this related to the breaking?
Actually, this is a title given in the early 70s by the people, but if you think that when the charge is ultra-relativistic, so it only decelerates while you fall into the black hole. So I think you can do some parallels with this breaking radiation in this case.
It's the balance, right? So the energy that's released is compensated by a loss in the particle energy.
Yeah.
also you only show the fluxes, right? Which is the important part to compute this Bremsstrahlung radiation, so Bremsstrahlung effect. But what about the time component? So it would be interesting to see how, you know, apart from the energy flux, how it is a waveform signal from these, considering these strings of particles that you consider in the end, say how it changes.
We have not investigated this, but there are plenty of works in the literature using the classical approach investigate this part of the.
Thank you, Caio. Thank you, João. Any more questions? Okay, so let's thank the speaker again.